Okay, good afternoon, everyone. Happy Friday, I guess. Everybody's always happy on a Friday and Monday morning blues, right? That's what they all say. It's got a lot of work to get caught up on the weekend. Anyway, let's begin. Let's continue with op amps. So, let's see. Amps. We stopped here. We had covered the fundamentals, looked at the analysis steps that we would apply, and then this was the example that I was going through, right? So just a brief recap again for this example. We have a op amp that has negative feedback and input signal being applied to the inverting terminal. Okay. And so it is a inverting amplifier, right? Signals going into the inverting terminal right here. So standard analysis is to first check whether there is negative feedback. Second is to apply KCL at the inverting terminal. And then third is to solve it. And so that's what we did here. So we had input current going in, feedback current, and then we had no current IN going into the terminal 0. Express each of these currents in terms of the resistor node voltages. And then once we do that, we can solve for VS, we can solve for VO. And you obtain VO as feedback resistance 80/16 times VS. Negative sign simply means that the output is inverted, is phase shifted by 180 degrees. So now let's look at, I believe I covered not this. Okay. All right, let's look at inverting, non-inverting, summing amplifiers and derive the relationship between the output voltage and the input voltage. We'll follow the exact same analysis steps. All of this is already there in the textbook too. A standard derivation. It's been around for decades. Pretty standard, so that we don't have to do it, but we need to understand how it was done. So we apply the exact same steps. First, we check for negative feedback. In output is connected back to the inverting terminal, hence negative feedback. So all other techniques will apply. So we apply KCL at this node. When you apply KCL, we already have our assumptions of virtual ground and virtual short concept. So we have the non-inverting terminal. The non-inverting terminal is connected to ground. Because the non-inverting terminal is connected to ground, we can say the inverting terminal is virtually connected to ground. And because it's virtually ground, we can say Vn is also equal to Vp. Right? Now this is a given assumption for every single analysis technique that we do. So we do not have to state it, but because I am instructing students, I will have this at the top every single time. Okay. But when you are doing an analysis, you have to state whether it's virtual ground, virtual short, and then just write it out. But for the most part, this is always automatically assumed. So because of the virtual ground concept, we can treat that node Vn as equal to 0. So now let's look at the current directions. We have I in or IS going in, and then here it splits in two. One goes through RF, the other one goes through IN. Okay, IN. Okay. Now, if the current's coming from the left, then it causes a voltage drop in this direction. So if you apply KCL, and I was to write the KCL, I would say IS is equal to IF plus IN. IS would be equal to Vs minus 0 or Ri, the input resistance. IF, the feedback path current, would be equal to 0 minus VO. Those are the voltages at either end of the feedback resistor. The feedback resistor is RF, right? This is RF. RF voltage here is 0 volts, and the voltage here is VO. And because my assumed polarity is plus on the left, it must be 0 minus VO divided by RF. So, does that make sense to everyone? Any questions? This would be RF. And of course, IN is 0. So IN is 0. And then it's the same equation as this one. Yes. So we are taking, let's see, question being asked is about Ri. So if I take the input resistor Ri, I have current going from the left. This means this is plus, this is minus. And left end of Ri is Vs, right end of Ri is Vn, which is 0 volts. And so we get Vs minus 0. And in chapter, was it chapter 1 when we did the fundamentals, right? Current always goes from high to low. It always goes from plus to minus. Alternatively, conversely, if you have plus to minus, then current is always flowing from, again, plus to minus. Point of entry is always plus, point of exit is minus. So if we assume a current direction, we can assign a polarity. If we assume a polarity, we can assign a current direction. In this case, we have power supply Vs. What happened? Just shut off. Okay, projector shut off in the classroom. Okay. Some glitch better. Okay. All right. Now, what was I saying? The question was about the current direction. Does that answer your question? Okay. Yes. So question being asked is if there is a resistor at the V out terminal, then yeah, we'd have to take that into account. But for most intents and purposes, if you're trying to just find V out, then we can simply take just RF and Rin, irrespective of what is connected at V out. So for this circuit, we won't take into account V out at all. As V out, yes. So even if it does have that, there'll be current flowing through that load resistor. So V out would have some value, but it does not affect that path for RF. Yes, actually, that's a good point. Whether RF is in parallel with RO, right? Yes, there are some problems and cases where we actually do that, but not for one of these classes. All right, something is going on with the projector in the room. What the heck? It's available just fine here at my end. Okay, let's see. Let's do this. Nope. All right, let's see. All right, so we have that KCL equation. We applied, not applied. We expressed each of these currents in terms of the node voltages at either end of the resistors. Then we rearrange the terms to get or obtain V out on one side of the equation and all other terms on the right side of the equation. And we obtain V out is minus RF or Ri times Vs. And that's all it is. Inverting amplifier. The gain is given by, let's see, gain of this amplifier AV. A in this case stands for gain, V is for voltage, so AV is equal to minus RF or Ri. Feedback resist, the ratio of the feedback resistance to the input resistance. So that's a design parameter. So if you have a 10 kilo ohm resistor and a 1 kilo ohm resistor, you configure them for 10:1. RF is 10 and Ri is 1. You have a gain of 10. You apply 1 volt input, you obtain 10 volts at the output. If you apply 10 volts at the input, you get 100 volts at the output. Would that be true though? If you apply 100 volts at the output, you get 1000 volts at the output. Would you obtain 100 volts and 1000 volts at the output? Energy cannot come from thin air. Okay, energy can only come from an applied voltage. In this case, the applied voltage is the DC power supplies plus VCC and minus VCC. Okay, so the op amp cannot provide any input that exceeds the power supply limits. The power supply limits are plus minus VCC. Whatever voltage we apply, output cannot exceed that voltage. So you remember the linear region of operation and the saturation region right here. Positive and negative saturation. The output of a circuit can never be more than the supply voltage. As simple as that. Okay, cannot be more than the supply voltages. So if your gain is 10 and you apply 10 volts at the input, but you only supply 20 volts VCC, well, we are not going to obtain 100 volts at the output. We will only obtain 20 volts at the output. All right. So your output saturates at a level of VCC. That is actually one of the homework questions. Anyway, so the design equation is valid only for the power supply limits, or only between the power supply limits. Does that make sense to everyone? Okay. But minus RF or Ri, feedback resistance to the input resistance. The minus sign again simply means it's inverted. Output is inverted. All right, any questions before I move on? Have you all used op amps in the lab? Not yet, but it's coming up next week. Perhaps. Okay. All right, next circuit up is the non-inverting. So the non-inverting amplifier, everything's the same. We have a feedback resistor, we have a input resistor line, but this time we are applying the input to the non-inverting terminal. Okay, hence non-inverting amplifier. First, check for negative feedback. Negative feedback is present, yes. Then In this case, we are not grounding either one of those terminals, right? I mean, inverting terminal is grounded, but it's grounded through the resistor RS. Okay, RS. And the reason I'm doing this is because the book uses these terms. So in order to avoid confusion for all students, I'm using RS exactly as the book does. Okay. If I was teaching this freehand, I would not use RS, I would use RI. Again, just to indicate it's the input resistance. That's all. All right. So negative terminal is connected to ground. It's also connected to the output via the feedback resistor RF. That's the RS resistor in the input line. And then this RG is simply showing you the resistor that is in the non-inverting input path. That's all. Okay. All right. VP, VN, and VG will all be the same because of the virtual connection concept. So if you're applying a generator voltage here, we can say it is going into the non-inverting terminal. It's going in the non-inverting terminal. The current entering the op amp is equal to 0. So there is no current going in, right? If there is no current going in, then the voltage drop across that resistor RG is 0. Again, I'll repeat. The op amp, one of the properties of the op amp is that it has infinite input resistance. So no current enters the terminal. And because no currents are entering the terminal, IN and IP are equal to 0. And because that is equal to 0, RG, the resistor in the non-inverting pathway, has a voltage drop of 0. It may as well not be connected at all. So anyway, the point again being that VP and VN are exactly the same. Okay, because of the virtual short concept. All right, so you apply KCL at the top node, inverting terminal. You have two currents. You have one current going in via the feedback path. The other one is going from RS. And so both those currents sum up to be 0. In this case, because this is connected to ground, you can say current is flowing in this direction. And then it's coming through RS and going to ground. And of course, IN is equal to 0. So you apply KCL at the end, we get IF plus IS plus IN is equal to 0. Actually, not that. IF is equal to IS plus IN. IN is equal to 0. And so we only have IF and IS. Okay. So we rearrange the terms, again, express each one of these in terms of the voltages. IF can be written as VO minus VG over RF. And that would be equal to IS. IS can be written as VG minus 0 over RS. If we take IF on the other side, rearrange the terms, we obtain this expression. Once we rearrange the terms to obtain an expression for VO, we obtain VO as equal to the input voltage VG times 1 plus RF over RS. has a similar form as the inverting. This is 1 plus RF over R in. That's typically how we would approach and write the gain. Leave space. So gain AV is equal to this. R in is same as RS. So gain for an inverting amplifier is minus RF over RI. Gain for a non-inverting is 1 plus RF over RI. Okay, 1 plus RF over RI. And that's the non-inverting amplifier. All right, any questions? Any questions at all? Okay. So from non-inverting, let's go to the summing amplifier, and then there's a difference amplifier. Okay. So if we look at the summing amplifier is a inverting configuration. The circuit diagram that we have is the inverting configuration. As the name suggests, it is an adder circuit, meaning it sums up all the input voltages that are connected at the input terminals. Now, one point about this is a summing amplifier can be both inverting as well as non-inverting. Okay. We are only looking at the inverting configuration, but the non-inverting configuration also works in exactly similar manner, right? So instead of one single resistor in the input path, we have 3, RA, RB, and RC, because we are applying 3 separate input signals, VA, VB, and VC. Okay, VA, VB, and VC. Each one of these inputs is connected to the op amp via its own resistor. So VA input is connected via RA, VB is connected with RB, and VC is connected with RC. All of these is then connected to one single node, and that single node is connected to the inverting terminal. Negative feedback is provided from the output back to the input via RF. And then the non-inverting terminal is connected to ground. So the analysis steps begin exactly the same way as the inverting amplifier. Since Vp is equal to 0, we can assume Vn is equal to 0. And Vn is equal to 0. We can apply KCL at Vn, and we can write exactly the same equation that we had for the inverting amplifier. We can have IA plus IB plus IC is equal to IF. IN is equal to 0, and IF is VO minus 0 or RF. We rearrange the terms to obtain VO on one side of the equation. When we obtain VO on one side of the equation, we see on the right-hand side, each single component at the input is summed up. We have RF or RA times IA, right? So that's IA. So RF or RA times VA. Then you have RF or RB times VB, and you have RF or RC times VC. Each one of those is an inverting input if it was by itself. When you connect and join them all together to the inverting terminal, it forms a summing amplifier. They're all added up, they're all summed up. But because it is an inverting amplifier, all the inputs appear with a minus sign at the output. Hence, minus VA, minus VB, and minus VC. If this was a non-inverting amplifier, non-inverting summing amplifier, the gain would be 1 plus RF over RA times VA. So it'd be 1 plus RF over RA times VA plus 1 plus RF over RB times VB. Because it's an inverting amplifier, you have a minus sign. Again, I want to emphasize, just because there's a minus sign does not mean it is subtraction. Okay. The signals are still being summed up. They are being added up. Minus sign simply represents the inversion. Minus sign is simply referring to the inversion. All right, let's take a pause. Let me know if you have any questions. Any questions from anyone? Okay. All right. So the next point in that equation is that what if all resistors at the input were the same? Meaning RA, RB, and RC were all the same. Well, it simply reduces our equation, right? So if all resistors are the same, then all inputs will have the same gain factor. Again, if all resistors, all input resistors are the same, then the gain factor for every single input is the same. That's the only difference, right? Because the feedback resistor is the same for all inputs. Doesn't matter however many inputs you have, the feedback resistor is exactly the same. It's RF, one value. The gain is determined by the values of RA, RB, RC, RD, and so on and so forth. So every single input resistance determines what the gain is for that particular input. So if they're all the same, and the name notation used is that it's RS, and we can simply write V out is minus RF over RS, similar to an inverting amplifier. And then the inputs VA, VB, and VC are all summed up. And so from this expression, it's quite clear that it's a summing amplifier circuit. All the inputs VA, VB, and VC are being summed up. And the overall gain applied to all signals is equal to RF or RS. RF or RS. And to take it one step further, if RF and RS are also the same values, then the gain is 1, and the output of the amplifier is simply VA plus VB plus VC. The input signals are simply being summed up. No gain applied. So it's a unity gain amplifier in that sense. And that is basically the third signal. Meaning all resistors in the circuit have exactly the same value, and output is simply a summation of all the input signals. All right, let's take a pause. Let me know if you have any questions. Any questions from anyone? Okay, then we have a difference amplifier. The difference amplifier, as the name suggests, is going to amplify the difference between the inverting and the non-inverting terminals. So this time we have a feedback resistor. We have a feedback resistor. We are going to call it RB. And we have two separate input signals, VA and VB. They are connected to the inverting and non-inverting terminal respectively. Okay. Inverting and non-inverting terminal respectively. All other techniques remain the same because there is feedback resistance. So feedback is applied from V out to V in to the inverting input terminal. So we can proceed with exactly the same analysis. So if you apply KCL at Vn, I can write this is IA and this is IB. Let's call this IF, feedback current IF going through RB. Once we apply KCL, we can obtain IA is equal to IF plus IN. IN is equal to 0. I can express IA as VN minus VA minus 0. VN. Getting confused myself. VA minus VN over RA, the input resistance. And then feedback resistance, of course, is V out. Let me write it out. So IA is VA minus VN over RA, which is equal to VO minus VN over the feedback resistance RB. And we take it on the other side and we obtain this equation right there. So we get Vn minus Va over Ra. That would be equal to Vn minus Vo over Rb. That would be equal to 0. Then we rearrange the terms. We get Ra plus Rb. Simplify the expression. We want to obtain an expression for Vo. So we take everything on the right side of the circuit. That's the next step. Then here comes the most important assumption. We have a resistor connected to the non-inverting terminal. And let's call this ID. This would be IP. It's a biasing resistor. It allows a pathway for the current to flow through ground. If we choose the ratio of RA to RB, the feedback resistance, to be the same as the ratio of RC to RD, then we can reduce VO. We can reduce VO to the difference between VA and VB. Okay. The gain is given by the ratio of RB to RA. That is exactly the same gain that we obtained for a inverting amplifier. Except in this case, because we are applying inputs to both the inverting and non-inverting terminal, it is plus VB for the non-inverting input, and it's minus VA for the inverting input. Okay, so it's VB plus VB minus VA. VB is applied to the non-inverting and VA is applied to the inverting terminal. So the gain of this circuit is given by those two resistors. Now, obviously, this is the case if the ratio of the four resistors is the same, meaning if RA, RB, and RC, RD have the same ratio. If we want a different gain, then we would stop at this equation. Okay. It's simply a rearrangement of the terms. That's all it is. Now, I don't expect students to memorize the derivation. Okay. These derivations have been around for decades. The greater minds that have come before us have analyzed these circuits. They have developed these circuits, and they have shown us how to analyze these circuits. Okay. What I want students to understand is the steps that we apply to obtain this equation. Okay. When you're working as an engineer, even in higher level classes like 300 level classes and 400 level classes, you'll encounter op-amp circuits which will be similar to these circuits, but they'll have different kinds of resistor configurations. But the analysis steps remain the same. You check for negative feedback. If negative feedback is present, then it's operating in the linear region. And then you apply KCL. Assume your current directions, apply KCL, keeping in mind the virtual short, virtual ground concept. And then you proceed to solve that equation. Every circuit will have different resistor configurations, so the equations will be different, but the steps, the analysis steps, will remain exactly the same. Those don't change. Okay, so again, I don't want students to memorize these equations, but you should definitely understand how we derive these equations and understand the steps. Does that make sense to everyone? All right, let's take a pause. Let me know if you have any questions. Questions? Okay. All right, last circuit is the voltage follower. One of the most simple, but also one of the most important circuits. All we do in the circuit is there are no resistors. Again, this is the simplest form of a voltage follower. You have an op-amp. There are no resistors in the circuit. All we are doing is we are taking the output, we are feeding it back into the input terminal. That's the connection. That's it. There is no other connection in the circuit. We are taking the output, we are feeding it or connecting it back to the inverting terminal. And then our input signal is applied to the non-inverting terminal. Okay. So essentially, the feedback resistor RF is equal to 0. Feedback resistor is equal to 0. And we are applying our input signal to the non-inverting terminal. Okay. So let's just follow this in the mathematical terms. Okay. We already know the gain for a non-inverting amplifier is 1 plus RF over Rin. In this voltage follower configuration, RF is 0, and there is no Ri or Rin. So what is the value of Ri? Feedback path from the output goes to the input. It's a short circuit. It's a short circuit wire, so the resistance is 0. And there is no input resistance connected. That means it's an open circuit. So what is the resistance? It's a lazy 8. It's an open circuit, so resistance is infinite. Short circuit, resistance is 0. Open circuit, it's infinite or infinity. Okay. So just mathematically speaking, without even analyzing the circuit on any level, if you just take the mathematical equation and plug in these values, what do you obtain? You have a non-inverting amplifier. The gain is 1 plus RF or RI. RF or RI is 0 divided by infinity. 0 divided by anything, answer would be 0, or anything divided by infinity, answer would still be 0. So gain of this circuit is just 1. So output V out is equal to V in. V out is equal to V in. And that's all there is to it. This circuit is also known as a unity gain amplifier. Unity gain simply means the gain is 1. It is also known as the isolation amplifier, isolation buffer. It's also known as the buffer amplifier. Okay. So now let's talk about what's kind of happening in the circuit. So we apply an input at the non-inverting terminal. We'd expect it to be amplified. We get some output, right? That output is fed back to the input. The property of the op-amp is that it will try to force both terminals to have the exact same value, Vp equal to Vn. So I'll try to force it to go to that value. Okay. So the input at the non-inverting terminal is, let's say, some Vp, right? Or here it's Vg. So let's just stick with Vg. Then the inverting terminal would also try to be forced to Vg. Okay, Vg. So every time the output wants to increase, because it's fed back into the inverting terminal, it's now being decreased proportionally, and the output follows the input. Hence, the circuit is also known as the voltage follower. Any voltage that we apply at the input is going to appear at the output because the output is following the input. Now, you might question, why would we need such a circuit? Which is the same question I had many decades ago. Okay. And the reason for this is in the keywords isolation and buffer. So in all electronic circuits, any kind of, let's say, any kind of electronic device you take, there are multiple stages cascaded one after the other. You'd have an input that is fed into a circuit, let's say circuit 1. Output of circuit 1 is fed into circuit 2. Output of circuit 2 is fed into circuit 3, and so on and so forth. As a real life example, let's just take the example of a audio amplifier, like an AVR, audio video receiver, for instance, that you found in any home theater system, right? You have an AVR. This AVR consists of a preamplifier, and you have an amplifier. The output of the amplifier goes to a speaker. Output of the preamplifier goes to the amplifier. And there is another external input going into the preamplifier. So there's like multiple stages in an audio section, right? This input could be anything. Could be a microphone, could be a Blu-ray player, could be the output of a computer, could be a guitar, could be anything. Anything can be an input. Whatever that input is, it is going to be very small by default. We cannot produce a large signal out of thin air, so it's going to be small. Because it is small, it will have very small voltage and very small current. So before that input is fed through the circuit, if you don't have any isolation, the next circuit, let's say in this case the preamplifier, or let's say you feed it directly into the amplifier, the amplifier is going to draw or pull a lot of current from that input circuitry. But that input circuitry cannot provide that high amount of current. Okay, so if we connect the input directly to an amplifier, it's not going to work. because the current in that input is very, very small. The voltage and current is actually very small. Okay. But before we increase the voltage, we need to increase the current. And to increase the current, we use this kind of voltage follower circuit. So this voltage follower circuit provides a buffer between two other circuits. It isolates them. Any current that needs to come between these two circuits is provided by that buffer circuit. So let's say this is your isolation or voltage follower or buffer circuit. Low current input. If you provide that low current input directly to your circuit, it's not going to work. So this buffer isolates it. If you give V in, voltage V in, tiny voltage, you would get the same voltage at the output, but you'd have high current output. Okay. So voltage is transferred as it is to the output. So the shape of the signal is not changing. But the increased current comes from this external DC power supply. Which in the case of the op amp would be plus minus VCC. Okay. So the op amp has plus minus VCC, external power supply. It takes the very small weak input signal, sends the voltage shape as it is to the output. So unity gain, there is no gain to the voltage, but the current is amplified. And the current energy, the energy to amplify that current, comes from the externally supplied DC voltages. Okay. And that's the purpose of the voltage follower. All right, so we're going to end class here today. I know we lost a few minutes trying to work on that projector in the classroom. I'll have to file a complaint as soon as we are done. And so I apologize for going over time. Quiz, as usual, on Monday, based on the topics that we've covered this week. That'll be from the homework problems and the reading assignments and the material we have covered this week. All right. So have a good weekend, and I will see you all on Monday. If you have any questions, send them to me today, tomorrow. Sunday, I'm going to be out for the, I'll be able to receive emails. I'll be able to answer emails, but I won't be able to log on to anything or any system and look at any problems. All right. So see you Monday.